tried to see how we're going to solve the system of inequalities, linear inequalities. We get a collection of lines, okay, and then we are going to consider the common area of the solution, if you like. So that was the example that we talk about it. You see, these are the equations, inequalities of the linear inequality. Each one of them would represent a straight line. So less than or greater than, we consider the area above the line or below the line. So if you have a several of these lines, then the common region is going to be the solution region, like this one. Then we talk about that these regions would have some important parts. We call them corners or vertices that we are very much interested in. So for example, this region, the boundaries are going to be these lines, and these lines are going to be intersection of the given lines. So their intersections are the one that we are going to call corners or vertices. Now the application that we are going to consider is going to be a system of, we consider these systems. These are going to be as a condition that we want to maximize or minimize something. Okay, so it's kind of optimization problems. So X can be, the type of, whatever it is, and the Y. Then I give you one example as an application. So what we do, that we call it a linear programming, is that we are going to be interested in an expression that contains X and the Y. It's a linear. We call it Z, that expression. Z equal to the 2X plus 3Y, for example. This is a linear combination, X and the Y. Under these conditions, we want to know what is going to be the maximum value or the minimum value that Z can have in this region, okay, in this region. So we're going to optimize or find the maximum or the minimum of a linear combination under this assumption, if you like, under this assumption. This is called linear programming. That's very old-fashioned and classic results. It dates back to the World War II, that they use this one, to locate or to switch the resources. Today, of course, we have a software that will do it for us nicely, but it's nice to know the classic results. Okay, so that's the idea of 6.6. We usually give 1 or 2 questions from this section, and it's nice to know what is the application of what you do with this, just sketching the graph. But there is an application for those sketching, okay? So it's a 6.6. A 6.6, the idea is called linear programming. Okay, this is it, the linear. It's going to be linear. Okay, and this is programming. What is the idea of a linear programming? So the idea is going to be I have to explain the problem, okay? So explain it in full details, and then we go for it. So let's explain it as we go on. We write it. A linear programming. Okay, a linear programming in 2 variables. In 2 variables. The variables are going to be X and Y. Okay, X and Y consist of, okay, it's going to consist of maximizing, okay, maximizing or minimizing, or maximizing or minimizing, maximizing, minimizing a linear objective function, we call it. A linear objective something that you want to do. Objective function. Okay, function of the form. You see that's going to be our objective function. This function will be denoted by z, and z is going to be a combination of x and y, linear combination. So it's going to be a times x plus b times y. When we say linear means it cannot be x squared or cannot be y squared. You cannot have something like x times y. That's exactly, this is what it is. Okay, and in this case, a and b are numbers. Okay, so where a and b are numbers. One of them can be zero, but not both of them. Okay, numbers, not both zero. If both of them happen to zero, so we get z equal to zero. So what? Nothing else. Okay, so this is going to be, so we want to maximize this function, z equal to the x plus by, under the given condition. Okay, we say subject. So we want to maximize or linearize it subject to the certain condition. Okay, it's going to be certain conditions, certain condition or expressions that we are going to use, or constraint. Okay, constraint or condition. These conditions are going to be expressed as a linear equation. Constraints, okay, these are going to be expressible, if you like, expressible as a linear inequality, linear inequality or inequalities, okay, in x and y. So you want to find the z equal to the ax plus y under some condition. You see, the condition are going to be under condition that, for example, x plus y to be less than or equal to 1, x to be positive, y to be positive, okay, 3x minus y bigger than 7. So there is going to be a situation and there is going to be a condition that we're going to impose on it, okay? So those conditions, we refer to them as constraints, okay, constraints. This is going to be objective function that you want to maximize or minimize. Now, how we're going to do it? Those inequalities that's given to us, you see these inequalities, we are going to graph it. We graph those conditions, okay, and we identify the region of the solutions. That region of a solution would have some corners or vertices, okay, which is the intersection of the boundary lines and the solution region. So you identify those vertices. Those are going to be points, x and the y, 1, 2, -1, 5, etc. So then what we are going to do is we are going to evaluate the z, find the value of the z at those corner points. So the corner points, we know x, y, we pick each one of them and we find the z. Then we get a bunch of numbers. The largest of those values are going to be the maximum of the z. The smallest is going to be the minimum. That's it. It's not the case that always you are going to have both of them. You may get minimum or you may not get a minimum, okay? So there is no condition or the theorem that will tell you that you know, you are going to get both of them, but we have to try. Okay, so that is going to be the idea. But if you want to get something historically, if you like, this is going to be the idea that's first it's used. Okay, that's history. So historically linear programming. Okay, linear programming. Linear programming involves, evolves That's the starting point. Okay, it's evolved or created as a technique. That's a good history. Okay, as a technique or method for solving. Okay, for solving resource allocation. Okay, this is it, resource allocation. Allocation of goods. Okay, of goods and materials. Goods and materials for the US Army. Okay, for the US Air Force. Okay, Air Force during the World War II. During World War II. You know that they have to get those locations, get those goods to the Europe mostly. So the number of the planes were restricted, and the number of the location or the goods that they want to carry. So they have to design something that give us the maximum, better of the system, if you like. They can do the job and do the excellent job, if you like. So they use this type of method. Today, of course, is used for designing the for designing the air traffic or airline traffic. Say today, this is the way we do it today. Today, it's used. Okay, it's used for airline. For airline scheduling. Okay, scheduling. And okay, and establishing, if you like. Establishing telephone lines. So as to give you an idea, I know there are many other applications in the modern days, but that's the origin of the problem. Okay, so this is going to be the way we are going to do it. Okay, so to do the job, the procedure is going to be we write the expressions, as I told you. We the procedure. I'm not going to write down the procedure, or just a brief one. I'm going to do it. So we get this information, we graph it, we find the corner points, we evaluate the z. Let's just give you just one hint. So this is going to be procedure. Okay, procedure for solving a linear programming problem. Linear programming problem. So basically, because those inequality would be given to you, so basically what we are going to do, we are going to sketch, okay, sketch the graph, the graph of each linear equation, okay, sketch the graph of the system, of given linear inequalities and find, okay, you are going to find the corner points. Find the corner points. Corner points or vertices. Okay, as we talked about before, okay, we get this one. Then what we are going to do is we are going to evaluate. Okay, the second one, you are going to evaluate the objective function, objective function as z, okay, at the corner points. You substitute. Okay, then the largest value. Okay, so this is going to be the largest, okay, the largest value of those numbers, if you like, the largest values of those numbers is going to be the maximum, and the smallest one, and the smallest value is the minimum. Okay, minimum of z, if you like. So you graph it nicely, just those corner points is the one that we have to find. Sometimes it takes a little bit more time to find it, but it's fine. Then we drop it back into the function z, we get a bunch of numbers. The largest one is the maximum, the smallest one is the minimum. It's a linear one. If you don't have a linear, we do it usually in calculus 3. There is another method for doing it, but these are going to be linear. So there are various methods to take care of the linear one. Okay, so I'm going to give you 2 examples. And for the application, we do the application when we get to that practice test, because it takes time to set up the applications, and but we do one for you. Okay, are you ready? So a situation would be created, the conditions would be given, and they ask for this maximum and the minimum. Okay, so this is going to be the case. We go with the first one. Okay, so this is, I have 2. So I do the second one first. So this is going to be our example. So we want to find the maximum, and the minimum of this is going to be your objective function z equal to, okay, it's going to be z equal to the 4x, okay, 4x plus y, okay, 4x plus y, subject to the following constraint. Subject, okay, to the following constraints. Okay, that's it. So what's going to be the constraint are going to be, that's it, x greater than equal to the 0, y is greater than equal to the 0, and 3x plus 2y less than 6. So these are going to be the information that we have. We saw all of them together is going to be a system of the inequalities that we have. So we have to find a solution to that system first and then come back and take care of it. Okay, so this is going to be the solution. So what we're going to do is we are going to graph. Okay, graph the system. And this is going to be the system that we have. We have x greater than or equal to the 0, y is greater than or equal to the 0. Okay, and we have 3x. I'm going to put equality for this one too. Okay, and we have a 3x plus 2y less than or equal to the 6. You see, this is the system. So x positive, y positive means you are going to be in the first quadrant. Okay, so you better focus on this one to graph this one first. Okay, so there you are. We have 3x plus 2y equal to the 6. We graph it. The x1 and y are together, so the intercepts would be the best choice. We put x equal to the 0, so this part would disappear, so the y would be 3. And we put the y equal to the 0, that gives it 3x equal to the 6, so x would be 2. So graph the line. Okay, so 0 and 3. So 3 units on the y is going to be 1, 2, 3. It's 1 point. Then 2 and 0 is going to be 1, 2. That's 2 and 0. Okay, get the line first. This is going to be the line. Get all the line first, then identify, the region in question. You see, then we have x positive. So this is going to be the x positive. Okay, this is x greater than or equal to the 0 in this case. And then we have the y positive. Okay, then this is going to be, you see the intersection that we're going to be interested in. So this is going to be, x positive is going to be, this is the x positive. Okay, and the y positive, this is going to be the y positive that we're going to have. Now you check to see where are you going to be. You see this is 3x plus 2y less than or equal to the 6. You can test the numbers, or just if you solve it for y, it's going to be less than equal to. Okay, it's going to be less than equal to, so this means you are going to be interested in the area below. Okay, so it's we can check the origin, or just solve for y, different way to do it. So that give you 6 minus 3x, and the y would be less than equal to the 3 minus 3 half of x. So you're going to be interested in the region below. Or you can test the origin to find out, the origin is going to be part of your solution. So for the line over here, you see the solution is going to be below. So it's going to be below the line. But you have to consider below this line, and when x is positive and the y is positive. So you could just consider this part. Okay, this part, because x is positive and the y is positive. This is less than x positive, y positive. So this is going to be the region of the solution. Any question? Don't make it complicated. You can color all of them to get it. You see x bigger than 0 is, this is the first quadrant. The first quadrant and the line. So for the first quadrant, everything here. But for the line is the region below the line. So below the line and the X and the Y positive. So that give you the region in question. Okay, any question? Now you have to identify the vertices. The vertices are going to be intersection of the lines. Okay, intersection of the lines and the region that you have. So you have 1 point here, okay, 1 point here, and the 1 point here. So you identify the vertices. If it's clear on the graph, you identify it. Otherwise, you have to take the intersection of the lines to have it. So in this case, the corner points are going to be, okay, so what is this point? This is going to be 0, 0. And we got this one by this intersection point. So that's a 2 and a 0. And this point is a 0 and 3. So these are going to be the important parts. So we have the corner points. We have 3 corner points. The corner points are going to be 2, 0. Okay, 0, 0, and the 0 and 3. These are your corner point. Now you have to find the objective function at this point and compare them together. Any question? So that was the corner points that we get. Now we bring the function and we are going to find it. So the z is equal to the 4x plus 5y. So check this. So the first point is going to be 2 and 0. So z would be equal to, okay, x is equal to 2, so that gives you 4 times 2, and the y is 0, 5 times 0, so that gives 8. That's the first number. At the second point, we get the 0, 0. If you put the 0, 0, z would be 0. Okay, because this is going to be just 4 times 0 plus 5 times 0 would be 0. Okay, and the last point is 0 and 3. So this is going to be, okay, 4 times 0 plus 5 times 3, which is equal to the 15. Okay, so that's it. So the maximum, the minimum, okay, the minimum of z is going to be 0. Okay, it's going to be 0 if you like at the point. You don't need, but sometimes they ask you to identify the points, but that would be fine. And the maximum of z is going to be at 15. It's going to be 15 at 0 and 3. In the application, these points mean something. When you get those combinations, then you realize that with this order, if you like, with this format, you are going to have a maximum numbers, but with this one, you are going to have a minimum. Then you can decide, what's going to be good for your, okay, for your problem. Any question? As you can see, it's not a difficult problem, and don't make it complicated, and especially this region, to get these numbers done. Okay, so I should give you another one because there is one case that sometimes it's happened. Just want to make sure you know it. Okay, so that was the first one. Just check the one that would have that property that we are going to be there. Sometimes it may not be possible to find the maximum and the minimum, or you may have, it takes a little bit more job. Okay, it's a kind of technical job that we are going to have. Okay, so I'm going to explain this one for you too. Okay, question? Nice, I see the application, very good one. So let's say a little bit technical one is going to be, looks like this one. You see, look at this region, we call it a bonded region. You see this one? This is a bonded region. So it's just bonded by these boundary lines. Boundary lines, that's why you get the maximum and the minimum. And this type of sets in calculus or in mathematical analysis, we call them a compact set. So if you have this type of bonded set or compact set, you are going to have the maximum and the minimum. But sometimes it's not going to be the case. So we give you this one. Okay, so let's check this. So we have the two type example that we need. So for this problem, we want to maximize this function. Okay, so we wanted to find the maximum, the minimum. Okay, find the maximum, and the minimum, and minimum of the objective function. The objective function is z equal to the 2x plus 5y. That's your objective function, and you want to do it subject to, okay, subject to the following. Condition or constraint, okay, and that is going to be the case. So what is the condition this time? Condition is a bit different. So we have a following condition. We have the x to be positive, okay, the y to be positive. Then you are going to have following condition. We have a negative x plus y is less than or equal to 10. Okay, then we have a 3x plus y to be greater than or equal to the 14. Okay, this is greater than or equal to the 14. And we have x plus 2y to be greater than or equal to the 8. You see, these are the conditions that we have for this problem. Condition, a little bit more conditions, but nothing to worry about. So we are going to consider this section, this system. So we're going to graph the system, graph the system. So what is going to be the system? The system would be, this is it. The system would be x greater than or equal to the 0, first quadrant, y greater than or equal to the 0. Then you have those lines that we talk about it. So we have a negative x plus y less than or equal to 10. Okay, 3x plus y greater than or equal to the 14. And the x plus 2y greater than or equal to the 8. Okay, so these are going to be the line that we have. Okay, so let's graph these lines. So we know that we are going to be in the first quadrant. So we start with this line. We start with that negative x. Okay, we start with the negative x plus y less than or equal to the 10. We solve for y so that we know that there is going to be the region in question. So that gives you x plus 10. Okay, so let's graph it. We graph the y equal to the x plus 10. So the points are going to be your intercepts. Okay, so we go with the x equal to the 0, the y would be 10. Y equal to the 0, the x would be negative 10. Okay, so that would give us the y equal to the x plus 10. Okay, so let's graph this one and keep it. So the intercept is 0 and 10. Okay, at 0 and 10, suppose this is 10, it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. That's going to be 1 point. And over here, negative 10. Okay, it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, so we connect these together. Okay, so this is going to be the first line. Okay, you identify that this line is y equal to, okay, the line is y equal to the x plus 10. And these intersection points, we know them. Okay, then we come back to it. So for this line, this is going to be below. Just don't shade it so far, and then you do all of them together. Okay, so, and we are going to be on the first quadrant, of course. So this is only the region that we are going to be interested in. Okay, so this is the first one. Let's check another one. Okay, so I'm going to check the next one is this one. So I want to check the 3x plus y to be greater than or equal to 14. So I solve for y. So that give me 14 minus 3x. Okay, so I have the line y equal to the 14 minus 3x. So I get intercepts for this one, x equal to the 0. So y would be 14. Okay, so y would be 14. And if you put the y equal to the 0, x would be 14 third. Okay, so we go and identify this is 0 and 14. So for the 14, I have to go a little bit up. So that was 10, 11, 12, 13, and 14. So that would be the 14. Okay, and the x is 14 third. Okay, 14 third would be 4 and something. Okay, almost 5. So it's going to be 1, 2, 3, 4. This is going to be the point. Okay, so this point is 14 third and 0. Okay, and this is going to be 0 and 14. Okay, now we connect them together. We connect, and this is going to be the line in question. Okay, so this line is y equal to 14 minus 3x. So it's going to be the third one. Okay, the third one, again, the region is going to be on first quadrant. And for this one is y greater than. So we are going to be here so far. You see, so far we are here above the green one, below the red one, and this is going to be the case. Okay, this point is going to be important one, then we have to find it later. So that's going to be the second line. Any question? So we bring the third one. So the third one is x plus 2y greater than or equal to the 8. We solve for y. So that would give us 2y greater than or equal to the 8 minus x. So y would be 4 minus 1/2 of x. Okay, again, it's going to be above the line. So we need intercepts. So this is going to be x and the y. Replace the x by 0. We need to find this line, 4 minus 1/2 of x. So if you put x equal to the 0, y would be 4. If you put the y equal to the 0, okay, y equal to the 0, x would be, okay, x would be 8. Okay, you are going to go and find out 0, 0, 4. So that's going to be 1, 2, 3, 4. This is 0, 4. And then 8 and 0. Okay, 8, 0. This is it was something like 5, 6, 7, 8. So this is 8 and 0. You are going to connect these two together. You see? And so what you are going to have is going to be y greater than. So greater than you are going to be here. Okay, so we already talked about it. For the red one was below, for the green one was above, and for this blue one is going to be above. So the region in question on the first quadrant is going to be this one. Okay, this is going to be the region in question. Okay, so the boundary lines are going to be, you start from here, you get to this point. Okay, this point is 8 comma 0. That's your first vertex. Okay, then you get to this point that you don't have it, you have to find it. Okay, and then we get to this point, then you have to find it. Okay, so these are going to be the case that you are going to have. You have to intersect this line. That's it takes a little bit more time, but that's the way it is. Okay, so this is 1. Okay, this is going to be 1 vertex. Then you get here, you see, this is going to be the intersection that you have. So you have to find these points. That's 1, 2, 3. And as you can see, your region is not bounded. It's open up. Since it's open, you find out that you cannot find the maximum, if you like, because it go on forever. But we are going to see it, why we cannot find it. So we have an extra job. The extra job is you have to intersect the blue and the green one to find this one, the green and the red one to find these points. Okay, so identify all the lines except the blue one. So the blue one is y equal to the 4 minus 1/2 of x. Okay, so what I'm going to do, I'm going to intersect these two lines to get the points, and then we have 3 points. You substitute to see if it's going to be the case. There is no maximum, you can see it here, but there is going to be a minimum that we have to find. Okay, any question? So you have a couple of these tab in your book, and it's not bad. You get to give you better understanding of what's going on. I'm going to intersect the lines. Are you done with this one? So I have to intersect 2 lines to get these. Okay, I intersect the, okay, this is it, this point first. The green one is going to be y equal to the 14. Okay, I got the y equal to the 14 minus 3x. That is the green one. And for the blue one, it's a y equal to, okay, it's equal to the y equal to the 4 minus 1/2 of x. That gave me the intersection point that I need. It's just a substitution method. We do it right away. Okay, so this is it. Let them two equal to each other. So it's a 14 minus 3x equal to the 4 minus 1/2 of x. And to get the x, you subtract that give you 10. This is going to be 10, and that's going to be 3x minus 1/2 of x. Okay, that give you 2.5, or the 5/2. So 10 is equal to the 5/2 of x. So x would be, so 20 equal to the 5x. So x would be 4. Okay, x equal to the 4, you substitute in one of these to get the y, substitute in the first one. So y would be 14 minus 3 times 4. That gives you 14 minus 12, which is equal to 2. So the point in question is going to be 4 and 2. This is going to be the one of the vertices or the corner points. Okay, so we identify this corner point as 4 and 2. So that give you 4 and 2. Okay. So we have to find another one. Okay, the other one is between the red one. Okay, between the red one, y equal to the x plus 10. Okay, that's the red one and the green one. Red and green. And the green is 14 minus 3x. Again, substitution method. It's going to be x plus 10 equal to the 14 minus 3x. Okay, you solve for x. That gives you x plus 3x equal to the 14 minus 10. So that gives you 4x equal to the 4. So x would be 1. X is 1. We substitute here. So that gives 1 plus 10, which is 11. So the other corner point is going to be 1 and 11. So you have 3 corner points. Okay, so this point is 1 and 11. So you have 3 corner points, you see, 8, 0, 4, 2, 1, 11. You substitute to get the result. Okay, so corner points. So the corner point is going to be the following. So we have 4, 2, 1, 11. Okay, and 8 and 0. 8 and 0. So bring your function. The function was z equal to the 2x plus 5y. Okay, so the z is 2x plus 5y. You get the number for each one of them. You have a 4 and 2. Okay, the z number is 2 times 4, 5 times 2, 8 and 10, 18. It's going to be 18 on one point. Okay, we go with the 1 and 11. 1 and 11. Z would be 2 times 1 plus 5 times 11. Okay, which is quite a lot. It's going to be 2 plus 55, which is 57. Okay, that gives you 57. And the last point is going to be 8 and 0. 8 and 0, when you substitute, it's going to be 2 times 8 plus 5 times 0. Okay, which is going to be 2 times 8 is going to be 16. I get the 4 and 2, which is going to be the 1. Okay, and at 8 we get the 16. Okay, that is going to be the case. You compare them together, the minimum is going to be 16. The mean is going to be 16, and you are going to get it at, okay, we are going to get it at 8 and 0. That give you the one. Okay, so the point is going to be You see in this case. So as you can see, the region is not going to be a bounded region. So you cannot get these maximum done because you see, look at the region over here. You see since the region is going to be an unbounded one, so you can think about it that you see over here, you can think about it. You can go on the x-axis, okay, and you just if you go after 8, all of them are going to be your corner points, if you like. When we get x and the 0, if you like. This x goes to positive infinity. You see in this case is going up, up, up. Since the region is going to be unbounded region, okay, unbounded region, so we claim that there is no, the region is unbounded, and there is no maximum. There's no maximum because you can go on the x-axis forever. So when x goes to positive infinity, if you like, you see, look at this one. When x goes to positive infinity on the x-axis, y is 0. So x goes to infinity. So the maximum would be infinity, if you like, but infinity is not a number. So I just wanted to see that, the tools involved. Most of the time, the region that would be given to you is the region that, the terms, you see the points are going to be on the x-axis, like the one that we did here. Look at this one. You see the intersection point was easy to find. These are going to be most of the time, this is the case. But just to know that this is going to be not complicated, the most involved one. So you have the idea really, if you want, you have it in your assignment. It shows, so you're ready for it. The application problems would be this type most of the time, rather than the first one. But it's not bad. It's a very good idea. As I told you, many applications. I have one application problems, but if I want to give you that one, it takes so much time, so I won't be able to do anything else. That's why I keep it, and I give you this one later on. It's a problem that you are selling coffee, for example, then you have different types of coffee. You know that they mix it together and they give you a new brand, if you like. So, and you make money. So you want to know how you're going to mix this coffee, two different types, one from Kenya, one from Brazil. Then you want to know how to match them together so that you get lots of money, or it would be good for you. So this is this type of problems. But I do one short one for you before your next test. This is linear programming 5.5.6. Okay, any question? So sometimes we skip this one or don't talk about it, but today you see this is it. These type of problems have been used basically, and you have a modern technology based on some classic results. So why not? And knowing it is going to be interesting. I teach calculus 3. I know that what would happen if you want to do a nonlinear one really on that course. So it's interesting to know. Okay, so that is chapter. Okay, we are done with chapter 6. So your chapter 7 is they talk about matrices and sometimes they go for it and they teach you some part of this one. But I just give you a sample really, because I know that what would happen for this type of ideas in future. So we give you a sample because we are within the system of the equations. So we give you a sample, a taste of what is going to be the application of these so-called matrices, okay? So what we would like to do is we would like to solve a system of 3 equations, 3 variables. Okay, three equation, three variables, but all the equations are going to be linear. So we want to know how we're going to solve it, but we need a short version of it. So I give you a break now just for 10 minutes just to refresh yourself. Okay, then we do that one to see if we can finish it today. Okay, so I have to give you a little bit preliminary of the idea of a matrix that we need, but it's a nice problem, and we give you two problems of this on the test, and of course on the final. Okay, so it's 8:16, 10 minutes. We come back and we take that problems too. Okay, see you then. Okay, let's get done with this section. Just checking, it must be 7.5 in your book. Just checking the section number. Yes, it is 7.5 in this new edition too. Okay, so we are going to look at the a method. Okay, a method. You know that if you have a system of three equation, three variables, a linear one, you know, in algebra, you can use the substitution method or elimination method to get the result. But that method can be summarized. Okay, it's the same method. We can summarize it so that not only for a system of three equation, three variables, but you can use it for any system you like. Okay, four equation, five equations. Okay, it doesn't matter. We can do all of them. So this is going to be 7.5. It's again of introduction to the concept of the matrices and eventually that application that we are going to be interested in. Okay, so very mild version of the matrices, the one that we need to do. Okay, so what's going to be a matrix or the matrices? Matrices. Okay, it's going to be a matrix for a single one and a matrices for the plural. So it's a kind of function. It's going to be a function that you drop the numbers, you know, that we drop the numbers into the function and we get the result. But the way we are going to identify the value of that function is, since the values are going to be finite, we're going to list them. We put them together. We put them together in just using a rectangular form, if you like, okay? So briefly, this is it, a matrix. Okay, a matrix is defined. Again, we talk about as much as we need. Defined as a rectangular ordering, if you like. This is it, rectangular is a rectangular array or array of numbers. Okay, so for example, the way we can arrange these are going to be, so we can arrange something like this is it. We can arrange it with 4 elements only. Okay, so this is it. The first element is going to be, we are going to have some row and columns. So the first member would be denoted by, it's just a notation. If you don't like it, you can ignore it. A11 means this is placed at the first row and the first column. And you're going to have A12, you are going to be in first row, second column. So you can have A21, okay, A21, you are going to be in the second row and the, okay, first column, and A22, you are going to be in the second row, second column. So this matrix would have 2 rows, 2 columns. So we're going to call it, we call it a 2 by 2 matrix. Okay, so we identify the row and the column. So that's a 2 by 2 one. Similarly, you can have another one. You can have in any range, but I'm going to be interested in so-called the square one. Means these two are going to be the same. So the other one that we are going to be interested in only is going to be 3 by 3. So officially, this is going to be the first part, A11, first row, first column, A12, first row, second column, and the A13. So that would cover the first row. And we continue getting the second row is going to be second row, A21, okay, A22, and this is going to be A33. I'm sorry, A23. So that will cover the first, second row, and the third row is going to be A31, A32, and the A33. So this would be generally a 3 by 3 matrix, 3 matrix. These are going to be the squares. You can have, various format. Okay, as you can see, each member would have two different indexes, one for the row and the other one for the for the columns. So in general, the terms Aij, if you like, Aij is going to be Aij are going to be called, these numbers are called entries of the matrix. Again, we are not going to have very much of these type of ideas. Okay, so in this case, I is going to be, for example, I can be 1, 2, 3, and in this case, j is going to be 1, 2, 3. Okay, we put them together as a function. So basically, you are going to have something like A is going to be a matrix, and these are the entries: 2, -1, 2, -1, 3, 5. You see that's going to be a 2 by 2 one. And if you would like, you can have a different format. We are not going to use this type, but you may have something like you see, like a 2, -1, 3. And this is going to be 1, 5, -7. As you can see, so this is a 2 by 2 matrix, 2 by 2 matrix. But over here we have 2 row and the second 3 columns, 2 by 3 matrix. Okay, if the row and the columns are the same, we say it's a square matrix. Okay, it's going to be a square matrix like this one. You see the square matrix. It's going to be like 1, 2, -1, 0, 1, 5, and this is going to be 1, -5, and 7. So this is going to be 3 by 3, 3 by 3 matrix. Okay, so matrix is going to be a kind of a place. So we can do quite a lot with these matrices if you like. We can add, subtract, multiply, divide, okay, all sorts of operation that you do with the numbers, you can do with this. These are functions. So with the functions, you can do whatever you like. But they are a little bit different function. Now, the quantity, I just quickly going to the part that we're going to be interested in. The quantity of a matrix that we're going to be interested in is called the determinant of the matrix. It's going to be a special number that would be useful for our purposes. So we go with that definition. So what's going to be the determinant? Determinant, okay? And this is it. What is going to be the determinant of a matrix? Okay, this is going to be the case that we are going to have. Okay, So the determinant of the matrix is going to be a number, and this is the way we're going to define it. So we define it by a 2 by 2 first. So if, okay, you make it easier notation to apply. If A is equal to, if A is equal to the matrix A, B, C, D, okay, is going to be, is a 2 by 2, is a 2 by 2 matrix. Okay, then the determinant of A, then the determinant of A is going to be denoted by, okay, is denoted by different notation. We can say that of A, determinant of A, okay, determinant of A denoted by determinant of A, and is going to be, and is defined by, so the determinant of this 2 by 2 matrix is like a cross multiplication, you see. This is the way we write it down. If you write the matrix in this format, means you want to find the determinant of a matrix, going to be A, B, C, D, and the result is going to be just a cross multiply AD minus BC. Okay, so the determinant of the A, or D, it doesn't matter, whatever you like, let's call it a D if you like, D, the determinant, one of these notations that we're going to use. Okay, so in this case, the determinant of A is going to be AD time minus BC. That is for the 2 by 2. Okay, it's going to be a special number, very useful in minutes. You are going to see it. Any question? Cross multiply A times D minus BC. So let's give you example. How we're going to find the determinant of a 2 by 2 matrix. Okay, so the example is going to be, example, the first one, we want to find the determinant, find the determinant of each matrix, the determinant or minant of each matrix, So the matrix is A equal to, this is it, is equal to the 3, negative 2, and the 6 and 1. Okay, cross multiply is equal to, I write it down so you know that, it's going to be 3 times 1 minus 6 times the negative 2. Make sure don't miss that negative sign. So this is going to be 3, and double negative would be positive, plus 12 equal to the 15. So the determinant of A is equal to the 15, and be done. Okay, any question? So that's going to be, the determinant of a 2 by 2 matrix. Give you another example. B equal to, okay, this is going to be 1, 5, and then we get a 0 and a negative 12. Okay, so the determinant of the B is going to be equal to 1 times negative 12 minus 0 times 5. So that gives negative 12. The second one is 0. Okay, this would be 0. So the det of B is equal to -12. Okay, any question? So that's a determinant of a, okay, determinant of a 2 by 2 matrix. So how about 3 by 3? We're going to use this definition to get the, okay, to get the matrix with the higher dimension. We need only 3 by 3. Okay, so what is going to be the determinant? Determinant of a 3 by 3 matrix. The way we do the 3 by 3, we reduce it into a 2 by 2. And we already got the 2 by 2. Is the way we do it. We're not going to give you any higher dimension, but if you have a 4 by 4, we reduce it to the 3 by 3, then the 3 by 3 would be 2 by 2, and then you have it. There's a formula for all of them, but we just give you, just one. Okay, we are not going to make it complicated. So there you are. So if this matrix is given to you, if A is equal to a 3 by 3, so this is the general formula: A 1 1, A 1 2, A 1 3. That's the first row. A 2 1, A 2 2, A 2 3. That's the second row. And the third row is A 3 1, A 3 3, sorry, A 3 2, and the A 3 3. So that's a given one. So the way we are going to do it is, there are different ways to do it. Shortcut, okay, quite a lot. But it's just a classic problem, so we're not going to make it complicated. So what we're going to do is, we are going to, this is, you have to reduce it into the 2 by 2. The way we can reduce it is, we are going to consider one of these row. You see this row? Then we are going to use this row to change it into the 2 by 2. So how are we going to do it? You see, look at this one. If it's going to be the case, then the determinant of A is going to be equal to, we pick these numbers, A11, A11. Then we are going to eliminate the row and the column that contains this number. You see, it's a A11. We're going to delete the first row and the first column. The leftover is a 2 by 2 matrix. So this is going to be A11 times the determinant of this matrix, A22, A23, A32, A33. You see, that's going to be the one. So we pick this number and we eliminate the first row, the row and the column. Then this is going to be minus. We pick the second number, A12. We do the same thing. We eliminate the row and the column that contain that number. So if you eliminate it, the leftover is going to be this matrix. A21, A23, A31. Okay, this one. A31 and the A33. Any question? So I pick the first number, eliminate this row and the column, the 2 by 2. I take the second one, eliminate the second column, and then 1, 2, 3, 4. And this is positive, negative, positive, plus, we take the third number, A13. Again, we eliminate the first row and the first column. So the leftover 1, 2, 3, 4. So that gives A21, A22, and this is going to be A31 and the A32. You see that's one. Now these 2 by 2, you can do it because we already talked about it. And you can continue find all of them to memorize it, but it isn't worth it really. Even when we teach that, that the big one in linear algebra, we don't go for it. So we reduce it to the 2 by 2, then we know how to do the 2 by 2. These are going to be cross multiply, and then we can do it quickly, and then we're done. Any question? You can pick any row to start with, but since you are going to just use it for one system, you just stay with the first row. And this just 3 by 3, you can do it for the 4 by 4, 5 by 5, etc. to get these numbers, okay? And for the problem that we're going to be interested in, this is your job only. You have to do it 4 times in one problem, okay? Just get to know it and don't miss any sign, any point, otherwise it's a straightforward problem. Okay, so example, let's do one of them. We want to find the determinant. Okay, find the determinant of the matrix. Okay, this is your matrix. Ax equal to, this is the given one, a 3 by 3. You have 2, -1, 3, -2, 5, 1, 0, 6, and -9. This is the matrix. Okay, are you ready? So we do it. Solution. Determinant of the A is equal to. I write it down, but in practice, we can do it quickly. Start with the first number 2. Bring the matrix. You eliminate the first row and the first column, so the leftover is 5, 1, 6, -9. That's a 2 by 2 one. Okay, always minus. The second entry is a -1. Put a parenthesis around it. Eliminate the first row and the second column. The matrix, -2, -2, 1, -2, 1, 0, -9, 0, -9. This is going to be your, okay, your second one. Any question? So it's a positive, negative, positive, plus, the number is 3. Eliminate the first row and the last column, so that give a -2, 5, 0, 6, 0, 6. Okay, we say we distribute it. Now take care of the 2 by 2 one. Cross multiply, so this is going to be 2 times. Let's do it right away, you see. 5 times -9 would be -45. Minus 6 times 1, 6. Or the 2 by 2, you just use cross multiplication. Okay, this is it. 5 times -9, -45, minus 6 times 1. Negative would be positive, positive. Do it. Times. -2 times -9 would be positive 18. Minus 0 times 1, 0. That's the next one. Okay, cross multiply. -2 times -9 would be 18. It's 18 minus 1 times 0 is 0. Okay, plus 3 times, multiply negative 2 times 6 would be negative 12, minus 0 times 5 would be 0.
Quick question.
Yes.
Is it always going to be, so when you're trying to find the, or when you get the 2 minus negative 1 and then the positive 3 outside of the matrices?
Yeah, it's a positive, negative, positive.
It's always going to be like that?
Yeah, that's fine.
So if you get like a 5 by 5, it's going to be positive, negative, positive, negative, positive, negative?
Yeah. You see, the reason is the way we do it, it's there is a negative 1 to the I plus j. You see, the I is the number of the row. This is the column.
Okay.
Okay. So I teach this one next term. You can register for that course, linear algebra.
Wait, if 2 was negative, would it still be positive, negative, positive, negative?
No. You see, it's a positive, negative all the time.
Right, but if 2 was negative, would that change anything or?
No, negative is the negative of the 2, whatever it is.
All right.
This is an extra negative. You see, it's an extra negative.
Yeah,
so it'll be a positive negative, so it'll be a negative.
Yeah, I mean, if it's a negative 2, it's a negative, so make it negative 2.
Yeah.
Yeah, you just change the middle, the sign of the second one. Okay, that's 1. You see, because the first one is going to be what? The first one is going to be first row, first column. 1 plus 1 would be 2. So negative 1 squared would be positive. So for the second one, you have the first row, second column. So 1 plus 2 is 3. So negative 1 to the third would be negative. But when we get to the next one, it's the first row, third column. 1 plus 3 would be 4. So that's why it's positive. You see, there is a special rule for all of them. But anyway, you just change the middle sign. Negative. Stay with the sign that you bring from here. So if it is a negative 2, it's going to be a negative 2 here. Okay, if it's a positive 2, it's here. But this one would change. This one would change because we have a negative here. Okay, so let's continue to get the numbers. This is going to be negative 51. And then you multiply that, give a negative 102. This is 18, and the last one is a negative 36. So this would be negative 18, and that gives you negative 120. So the determinant of the A, that of A is a negative 120. And that's going to be the case. Okay, any question? So that would be 1, we get the 3 by 3 one. Okay, I give you another one. Just give you a couple of minutes to see if you can do it yourself. Can you give us the answer for this one? Want to make sure you know it, or do you get it? The matrix is 3, 4, negative 1. And that's a 4, 6, 2. And that's a 8, negative 2, 3. Can you try it to see if you can get the numbers? Go with the first row, that's going to be 3, you eliminate. So that would be a matrix, and you get the second one. Okay, anybody got the answer? Okay, that's sweet. The answer is 138. Let's see. You see solution. So the determinant of A is equal to, the first one is 3 times. Okay, 3 times. You see, that's going to be the one. It's a 6, 2, negative 2, 3, minus, minus 4. Eliminate the first row, second column. So that gives you 4, 2, 8, 3, plus, it's a negative 1. It's a negative 1. And that's going to be 4, 6, 8, negative 2. Okay, positive, negative, positive. Now it's going to be 3 times, cross multiply. 6 times 3 would be 18, minus negative 2 times 2 would be a negative 4. Make it into positive. Okay, it's going to be, I write it down. So this is going to be negative 4 times 3 would be 12, minus 16. And this is going to be minus, and that's a negative 8, minus 40. Okay, this is it. It's going to be 48. Okay, so simplify it. That gives you 3 times 22, minus 4 times negative 4. And that's going to be minus, and this is going to be negative 56. So if you put them together, that gives us 66, 16, and 56. The result, 138. So the determinant of the A is going to be 138, and be done. Okay, so this is the way we're going to find the determinant of the given matrix. Okay, any question? Now we are ready to to apply it, to get the application. The application that we're going to have is solving the system of the equation. You see, when you do the system, the easiest way to do it is just elimination method. Remember, you eliminate x and the y to get your result. To eliminate it, you try to have the coefficient of the variables that you want to eliminate is going to be opposite of each other, and you do that job. If you put them together, really, you have a something in terms of the determinant, your final answer. So and this is going to be the answer in terms of the in terms of the determinant. The result was done by an English mathematician. His name is Cramer. So that's why we are going to call this one Cramer, if you like. It's it, Cramer's rule. Okay, that's the name that you have to know it. So we are going to use matrices, if you like. That's an application. Matrices can be applied. Okay, can be used or can be applied to solve. Okay, to solve a system of the equation. A system of course, a linear equation. Linear linear equations. Okay. Now the method is going to be, you see, the method is going to be called, the method is called Cramer's rule, and this method based on, okay, is based, okay, on the concept, of the determinant, okay, of the determinant. Now, usually do the 2 by 2, get the numbers, but let's do the 2 by 2 first. Then if you like it, then we can consider the 3 by 3, which is the, see, this is the one that we want to do it. So to get an idea of the formula, you're going to consider this system. Consider the system. So the system in question is this one. Okay, ax plus by equal to, let's say, is equal to the s. And the second equation is cx plus dy, let's say, is equal to t. Okay, now, if the determinant, you see, if d is going to be determinant of this coefficient, you see, is going to be determinant of a, b, c, d. The coefficient of a matrix, you know that this is going to be a 2 by 2, so it's going to be AD minus BC. If this is not going to be 0, because if it's going to be 0, we cannot solve it. If this is going to be the case, then if you use the addition method that you use in algebra, you arrive at this nice formula. The formula is going to be then x is going to be equal to the determinant of this matrix. You see, this is going to be the one. Look at, you see, this is the first row is going to be A and C. We are going to remove this one by S and T. So it's going to be S, and this is going to be T. And the second one is unchanged, is the B and D. But we divided by, okay, we divided by D, the determinant of those, okay. This is going to be the determinant of this matrix, okay. And the Y, what is going to be the Y? The denominator is D again, but the top is this matrix. You see, this is the Y, the second variable. So what we do is, we are going to replace the coefficient of the Y by the constant term S and T. So the first part would be AC. Okay, the first part would be AC, but the second part is going to be ST. See? And you know, if you just use the addition method that you want to eliminate the x, is going to be exactly the same formula. Okay, so we find the determinant of a coefficient first. These are the coefficients. We check if it's not 0, because if it's going to be done the denominator would be 0. Then you have to consider something else. And so what's going to be on the top of the x? For the x, you replace the first column, x column, we call it, the x column by the constant term. The second one would be unchanged. For the y, you replace the y column, okay? Replace the y column by the constant d to get the results. Okay, so this is going to be d equal to the 0, d not equal to the 0. If d happen to be equal to the 0, then you have to consider, okay, other conditions that I'm going to talk about it later. But we are going to summarize this formula. Okay, we call the top one. Okay, this is it. Suppose that's easier to to memorize it. This top one we are going to call it a dx. So the dx is going to be the determinant of this matrix, the top. So what is x represent? X represent that you are going to change the column of the x with the constant. And the second column is going to be the same. Okay, it's going to be b and the d. Okay, and we are going to have a similar one. We call the second one dy. Okay, we call it a dy. So what is the dy? The dy is that matrix determinant. The first row is going to be a times c, but the y column would be changing to the s and t. S and t. So if this is going to be the case, simply your x is going to be d sub x over d, and your y would be d sub y over d. Easy to calculate or easy to remember for this type of ideas. Okay, this is a 2 by 2 one, if you like, for the determinant of okay, to get the a solution of this system. Okay, are you done? Then I explain it to this is 2 by 2. 3 by 3 would be the same one. We do it the next time, but we have to finish this one first. Okay, so the conclusion is going to be, the conclusion is that if d is not equal to the 0, then x equal to the d sub x over d, and y equal to d sub y over d are going to be our solutions, okay, of the system. Okay, so we get one solution. Now what would happen if d is equal to the 0? If d is equal to the 0, you see, if d is equal to the 0, then you look at the top. Okay, if d is equal to 0, one of them is going to be non-zero, and dx is not equal to the 0, or dy is not equal to the 0. You see, suppose this is 2 and this is 0. You know that 2 divided by 0 is undefined. So in this case, we say the system has no solution. The system has no solution. Remember, in algebra, we say the system is inconsistent, means there is no solution. So what's going to be the third case? If d is equal to the 0 and the dx is equal to the 0 and the dy is equal to the 0, you see, in this case we get 0, 0, 0, 0. If this is going to be the one, as like in algebra, the system would have infinitely many solutions. So the system has infinitely many solutions. Like exactly like they have, in algebra, you know that the first part we say the system is independent, the system is inconsistent, the system is dependent. So we are not going to use those expressions and just be happy about the, just tell us what's going on. Because when you get the 2 by 2, you may have a similar one for the 3 by 3 one. Okay, let's give an example for this one and we finish the 2 by 2, then we can talk about 3 by 3. 3 by 3 is the same thing, it's the same formula. It takes a little bit more time. Okay, so this is its example. Very nice method. This is just a 3 by 3. You have, a 5 by 5, 10 by 10, and many other application of this formula. Okay, so we want to solve each system. Solve the system. The system by Cramer. Cramer's rule. So this means you are not going to use any other rules, remember. You have to use the Cramer rules only, no algebra. Okay, this is it. Let's try this one to see how far we can go. It's a 3x minus 2y equal to 4. And this is going to be 6x plus y equal to 13. That's it. You have to find the d first, the determinant of a matrix of the coefficients. Okay, so let's do it. D first, D, determinant of coefficients. They must be all on one side of the equation, remember. It must be in a standard form. So this is 3, -2, 6, 1. Okay, 3, -2, 6, 1. Find the determinant, you know that. 3 times 1 is 3, minus -2 times 6, -12. So that gives it 3 plus 12, which is 15. So the determinant is 15 and it's not equal to the 0. So we go for it. Okay, we're going to find d sub x. What is d sub x? You're going to replace the first coefficient, first column, by the column of its constant. So this is going to be 4, 13. The second one is as is, -2, 1. Cross multiply, so that gives you 4 minus -26, which is going to be 30. So we are ready to give us the x. X is d sub x over d. 30 divided by 15, that gives us a 2. So x equal to 2. Any question? Because the x is dx over d. Find the dy. dy equal to matrix of the coefficient. You have to change the y, column of the y. So the x is at 3, 6. We change column of the y into the constant. Okay. Now we find the determinant. 3 times 13, 39. Minus 24. Okay, this is it. So this is going to be equal to 15. So what's going to be y? Y is dy over d. 15 over 15, which is 1. So y would be 1. That's it. So the solution, x comma y, is equal to the 2 and 1. And then you're done. Any question? So that's a 2 by 2 1. And then I just give you 1 more minute. I'll give you another one. Then this is a 2 by 2. We are interested in 3 by 3, but you have to take care of this one first. We give you one from each on the test. Okay, let's see what would happen if things goes otherwise. Finish the 2 by 2 one. Okay, let's consider this system. Okay, what's going to be the system? The system is 3x minus 2y equal to 4. Then we have 6x minus 4y equal to 0. See what's special about this one? Okay, so form the D first, the matrix of the coefficients, 3, -2, 6, and -4. Cross multiply, 3 times -4, -12, minus -2 times 6, -12. So that gives -12 plus 12 equal to the 0. D equal to the 0. And some people quickly they say there is no solution. No, you have to find the others. Remember, if you have a dx or dy to be non-zero, yes, you make it all of them 0. Then you are going to have infinity many solution. Okay, so you have to continue. Okay, you have to continue. Go for dx. D sub x is equal to, we have to change the column of the x with the constant. The constant is 4, 0. 4, 0. Okay, so the column of the y would be unchanged. -2, -4. Get this one. So this is it. So that gives a -16. -16 minus 0, which is a -16. It's not 0. So the dx not 0. You're not going to continue. And the d not 0, so this means this is impossible. There is no solution. Because if you want to find the x, remember the x is dx over 0. Dx is -16, but the d is 0. It's impossible. Okay, but if this happens to be 0, you have to continue to find the dy. If all of them are zeros, then there are infinity many solutions. And that's it. Any question? That's a 2 by 2, 3 by 3 is the same. Okay, then I write the formula for you next time, and then we test it. There are many applications of this formula, but we leave the application for, let's see, after the test, or maybe we talk about it. So that's it. So I post